Welcome students to a lesson with Mr. Kinnett again. We're moving on to 12.3 in our textbook. We're learning about area of composite figures. And something you're going to want to keep in mind as we go through this whole lesson is you're trying to be able to answer this first reflection question. What angle does the base and height of a shape always meet at? Go ahead and pause here and copy down what you see. Hey, welcome back. So we will be learning how to find the area of composite figures by breaking them down into smaller shapes. And by the end of this lesson, you should feel confident on how to find the area of composite figures. And really, composite just means made up of other shapes. So we're going to be looking at complex shapes and trying to break them down into their smaller shapes to solve it. So right on our right page here, we have a bunch of shapes we're trying to learn, and I tried to simplify this as much as possible. Many of us may have learned a special formula for parallelograms, 4 squares, and 4 rectangles, but then you may not have been taught these 3 things are similar. A square is a type of parallelogram, as is a rectangle. A square is also a type of rectangle. It's just a special type of one. So they all 3 have the same formula. And the area of any parallelogram, square or rectangle, is its base times its height. The area of a triangle, well, think about it. If we were to cut one of these squares in half, how many triangles exist within there? Yeah, you're right, it's 2. And that's why when we find the area of our triangle, we have to cut the base and the height in half. That's because inside of any parallelogram, square or rectangle, you can create 2 triangles. So to find the area of one triangle, you take the base and the height and cut it in half. So again, these formulas come from each other. I'm going to jump ahead to the next page and go ahead, pause here and copy down what you see. Okay, welcome back. So our last 2 shapes are trapezoid and circle. And we're recycling the circle lesson we've already seen. I just wanted to get it on the same note for you. So on trapezoid, we have this, what may look like a more complex formula, but I think we can figure out why it looks like that. So why do we have to add base 1 and base 2 together and cut them in half? Yeah, if you said we had to average the base's lengths, that's why we're adding them together and cutting them in half. We're just finding the average base length of the trapezoid. So that's why the area of a trapezoid's formula is 1/2 base 1 plus base 2 times its height. So and the last shape we're going to use in this formula or in this chapter section is circles, which is just like the last one. The area of a circle is pi times the radius squared. Okay, so now how do we do this? I have a couple quick steps here that we're going to recycle over and over again. Go ahead and pause here and copy down what you see. I'm actually going to slide ahead to the next one so you get the copy down the problem as well. Go ahead and copy down what you see. Okay, welcome back. So anytime we're doing the area of composite figures, step 1 is going to be trying to break the larger figure up into smaller, recognizable figures that we have formulas for. So any student will have the ability to cut up their figures in different ways. The goal is to do it in the most efficient way. And again, it can be different for some students versus another student, but if you do cut them up correctly, we'll end up with the same answers in the end. Once you have cut them up into different shapes, the next goal will be to find the area of each smaller portion. So once we've broken it up into smaller portions, we're going to find the area of each of those smaller portions. And then the last step is we will add together the shaded in regions, and we would subtract the areas of the cut out parts. So in that shape example from example 1, the area of the white rectangle, we would have to use subtraction for that area, and we would be adding the area of the other rectangle, the big green one that goes around the white one. So let's start trying to apply our steps to example 1. How many shapes do you see? Yeah, I see about 3 shapes. I see a triangle in this upper right. I see a really large green rectangle, and I see a very small white one. That's not the only way you could cut this up into different shapes. We could use dotted lines to make a rectangle over here or over here if we wanted, but those would just add a couple more steps. So we're going to try and keep it as simple as possible and keep it to those three shapes that we can see there. Now you may notice that this triangle over here seems like it doesn't have a base, but we can find that missing side. So let's do the triangle first. And just like our other problems, I like to keep myself really organized here. So we're going to list our shapes. We're going to have a triangle. I'm going to go to another page here to have a little bit more space. We're going to have a rectangle. And I'm going to call it rectangle 1 because we're going to have also a rectangle 2. And notice I'm leaving space to do math below each of these little sections. Again, it's going to be important that we stay organized during these problems. Let's start with the triangle. Well, first things first, we should always, whenever we use a formula, we should write it down. So the area of a triangle equals 1/2 times its base times its height. And when I'm looking at the shape up there, it looks like I could find the height of the triangle, but it doesn't look like there's a base. But I want you to look at the shapes. Remember, mathematicians are efficient. They give you the bare minimum amount of numbers necessary for you to know all the numbers that are supposed to be there. Is there a way of figuring out what the length of this base is given the other numbers on the shape? Yeah, there is. The base on the bottom is 15 feet. And then we have this measurement on the top, which is 12 feet. But we know rectangles need to have the same length on the bottom as they do on the top. So to find the length of this missing side, we just do the 15 feet, take away the 12 feet on the top they listed, and we now know that it's 3 feet. So to find the missing sides, we use those parallel sides and our understanding of the shapes to find the measurement they didn't give us. So the base of this triangle in the upper right is 3 feet because 15 feet's the bottom base, 12 feet's the number they gave us on the top, and we knew that it had to equal 15 feet, so there had to be 3 more feet there. So now we have all of our numbers. So now we're just going to substitute. The area of the triangle equals 1/2 times 3 times 3. And that's going to get us, after doing our order of operations, 9/2, or to make math easier in this lesson, we're going to use a decimal in this case, 4.5. So we're going to use its decimal to do the addition a little quicker. Now, what unit should be on this area? What do we get when we multiply a foot times a foot? Yeah, it's a foot squared. So the units for area problems have the unit of a square on it. And if you ask me in class, I can show you why we call it a square as a nickname for the power of 2. So that was us finding the area of the triangle. Now we have to find the area of the rectangle 1. And for rectangle 1, I'm just going to call it the large one. And the formula for a rectangle is area rectangle equals base times height. Notice I'm using subscript through these lessons so that I understand which areas I have. And since I have 2 rectangles, I should probably use the number 1 next to my R. Okay, what is the base of the large green rectangle? Yeah, it's 15 feet. And what's the height of the really large rectangle? Yeah, it's 9 feet. So we're just going to substitute into there. Do a little bit of math, and we find that the area of rectangle 1 is 90 times 15. That's 135. Oh, what's my unit again? What's a foot times a foot get us? Yeah, it's feet squared. Okay, so we're getting each of our little pieces, and notice I haven't boxed any of these numbers yet, because none of these are the actual answer yet. We have a lot of math to do to get our answer. So now we have to find the area of the rectangle 2, and I'm just going to remind myself that's the small one. And the area of rectangle 2 equals base times height still. We got to substitute in there. And what is the base and height of the rectangle 2, the small white one? Yeah, you're right. It's 8 and 7. So the area of rectangle 2 equals 56 feet. And yep, we were right. We need that square there. Okay, so now we got the area of each of the smaller figures. So now we're on step 3. We have to add together the areas that are shaded in and subtract the areas that are cut out. So we're going to have to add rectangle 1, the large one, and the triangle together, and then subtract the smaller one. So I like to use formulas. So we have area of rectangle 1 plus the area of the triangle minus the area of rectangle 2, the small one. And now I'm just going to substitute in there and do our math. 135 feet squared plus 4.5 feet squared minus, because it's cut out, 56 feet squared. And once we do a little bit of that math there, we get 83.5 feet squared. And that is the area of our composite figure, the shaded in part. So all the problems are going to follow the same pattern where we break our shapes up into smaller shapes we have formulas for. We're going to add shaded in shapes and subtract out the cutouts. So I'm going to jump 2 problems ahead here. I'm going to have you copy these 2 examples down. And again, it's really vital you leave space. We're going to have to draw a picture for example 2 and then have room for the math. In example 3, I got the picture there already, but we still need room for the math. So please leave space. Go ahead and copy down what you see, and we'll finish these problems in class. Thank you again, students. If you have any questions, please write them down in the question column. Those are great to ask in class. I'll see you soon.